Good afternoon, everyone. This is Mr. Couple. Today I'm with my IBSL Year 2 students, and we'll be learning about thermal power plants or thermal power stations. There are three main ideas for the lesson today. Number one is I want to talk about how most power plants or thermal power plants use water to produce steam and then turn a turbine to generate electricity. We also want to talk about Sankey diagrams, which show the energy transformations and are used to calculate efficiencies. And the last thing I want to talk about is how nuclear reactors work. Specifically, three components of the reactor are the fuel rods, the control rods, and the moderator. Man, I'm like all messed up. Anyway, the way I wanted to start off was just by sort of continuing what we've been discussing around energy sources. So I wanted to show you guys this interesting table that it was in the textbook. So this is the main sources of energy, and these are world averages in the year 2011. So what do you guys notice about this chart? Like anything you want to just chip in about like things that are interesting that you see on this chart?
It's a lot of oil production,
A lot of oil. So where is most of that oil going to being used in?
like power plants for electricity.
Not so much.
Car, not just the. Well, yeah, cars.
Yeah, transportation. So like jets, ships, cars. That's where we're using that most of that oil. So 32% of our energy that we produce is roughly transportation. What else do you guys notice that's interesting here?
It's a surprisingly large number of biofuels. Actually, I would have thought that would be less.
Yeah, 10% worldwide. That's a ton. That is a lot. Yeah.
It's surprising
Also,
how
Yeah, solar is
solar
not on there.
just like
it's surprising
Whereas
how little is being produced by nuclear.
yeah, nuclear is very small, only 6%. But I mean, is it surprising this is a world average? So what is it about nuclear that's making it so low across the world?
It's expensive to develop and get started
Right. It takes a lot of technological infrastructure within your society as far as like educational systems, research and development. It's very, very expensive to do that. And so very few countries can actually afford to do it. And then also notice that the thing that sticks out to me is like these ones that are really low, those are the ones that are quote clean as far as greenhouse gas emissions. The ones that are abundant, like over 80%, are carbon dioxide emissions. So when I first saw this, I was like, oh, well, this is 2011. Like it has to have changed since then, right? Like this is old. This is almost 10 years old. It's got to be different. And so then I went and pulled up some newest information. So here's a graph of our energy consumption worldwide by source from 1965 to 2018. This is a little bit more recent. And then what just stands out to me on this graph is how little has changed. I mean, it's pretty flat. It's not perfectly flat, but it's more or less flat. And that's kind of depressing. What do you guys think?
kind of maybe like I don't know. It feels like maybe the media is sort of like overstating how much is being done when actually more needs to be done, or something like that.
Right. Like you can see like a very gradual increase over here in the renewables like of late. Like there's a very small increase over here, but it's like it's not even going to make a dent worldwide. Like the amount that the renewables have increased here is just it's so tiny. It's really sad. This is just the United States, so getting rid of the rest of the world, and it's really no different. I mean, it's not that much different as far as the world versus the U.S. So this isn't just like a something that's exclusive to the worldwide average. This is we, one of the most developed countries in the world, are equally having difficulties getting those renewable energy sources online. There's been a lot of progress, but we're just nowhere near.
because people are stubborn and don't like change, and people want to make money.
Well, yeah, but also it's just easier. It's easier to, power cars off oil. You notice like almost a third of our world energy consumption is oil. So when you talk about like all the gains in power production with renewable power like wind and solar and stuff like that, that's sort of being dwarfed because none of that energy is going into our transportation because we haven't made large scale shifts to using electricity to power our cars yet. So I imagine like as electric vehicles start to get more popular and more feasible for the average person, I think you're going to see this oil just start to drastically shoot down. And until that happens, nothing's really changing. Here's China. Just shout out
Yeah,
ideas there.
China is
They're not.
useless.
They're using like very little gas, which is interesting because like a lot of the other world, it's like almost like a third of the rest of the world's consumption is gas.
Right, like for the US, you can see we're using tons of natural gas, but then China is mostly working with coal here. Like they're just predominantly using coal. And I'm not really sure. I should have done some more research on that. I hadn't thought about that, Joel. So I'm wondering if maybe China just doesn't have access to natural gas resources, which is mainly through the hydraulic fracturing, like fracking, which is where the US has just exploded recently, which is why you've seen this huge explosion in the US in terms of using gas. It's because of the fracking boom that has taken place over the last decade, which has also
No
been
wonder China
contributing
is
to
covered
the
in
yeah. So yep. Oh yeah.
no no wonder China is covered in smog all the time.
Yeah, it's been a major problem for them. The other thing is like this isn't showing us the total production. This is just showing us a percentage. So if you looked at total production, I'm going to show you guys that graph a little bit later. But if you want to go look up data for other countries or any other graphs, you can go to this site. It's called ourworldindata.org/energy, and you guys could go check it out for all these graphs. All right, so as you can see, the vast majority of our electricity is generated through burning fossil fuels. Like I said earlier, it's about 80% worldwide. And so it's kind of important to know and understand how thermal power stations work because we're mainly burning fuel. Like you can see here, we're sticking coal into this power plant, this power station, and we're burning the coal to generate electricity. And so we want to really kind of understand that a little bit better and sort of see like, what's involved in this process. So basically, thermal power stations are power stations in which the primary energy source, so whether the primary energy source is nuclear or coal or you know natural gas or whatever you want, that the primary energy source is first converted into internal energy or thermal energy, and then it's converted into electrical energy. And so it takes a large station to do this. Like there's a lot of pieces to this. So like you got to burn the fuel, you got to extract the energy out. So now we've turned it into internal energy. Then you take that internal energy, you use it to boil water inside here. Like those little pipes are full of water. You can see the water has come from here up into this pipe. So we fed this thing with water. You're basically boiling this water, sending it to a turbine. The turbine's going to spin. That rotational or mechanical energy goes to a generator. It then spins some magnets, changing magnetic fields, generating electricity, and then it gets to a transformer, which boosts up the voltage and then sends it off to the grid. Then what also is happening is once that heat is extracted from the steam, you let the steam condense back into water again, and then that starts this cycle over again. But you also have to cool down that steam. You have to cool it down, and so that's what these cooling towers are. Like you've probably seen these things around. They're like iconic images of like these structures that are helping to cool off the water, and then usually that ends up you end up pulling in like cold water from a lake into the cooling tower to help you like cool off this stuff. And you send that cool water in here, it cools off. There's like a little heat exchange, like the cold water goes in, and then the warm water comes back out again, and then you let that evaporate out. And that's what you're seeing in those. I should have shown a picture, but that's what you're seeing when like all that quote smoke is like coming up out of this cooling tower. It's actually just what am I trying to say? Water vapor that's rising up off there. Now the stack over here, that's where you're seeing like those huge pollution clouds coming out. But the cooling towers are just releasing water vapor. All right, that's my basic explanation of this diagram. It's a thermal power station. Do you guys have any questions? So the main takeaway from this is all that you really change in a thermal power station is you just change this part. So you change what you're putting in. All of this other stuff out here like basically stays the same, whether it's a nuclear power plant or coal power plant. That's the basic design. Is you're just going to change the input. This cooling cycle is called the Rankine cycle. IB doesn't want you to know that, but I just thought you guys should know. So the process of like turning steam, condensing it back into water, and then recycling it back through, like where you take the steam and then recycle it back through again, like that cycle is called the Rankine cycle. Rankine cycle, and it's used in every modern power station, thermal power station. This is a picture of a steam turbine, so you guys can get a sense of the scale of these things. Once again, that's the turbine that's inside here. That's the fan, the giant fan that you're using the steam to spin. That's generating the electricity. So those things are massive. They're gigantic. So like I said earlier, the greatest variation in the design is with the different heat sources. So here's what a natural gas power station looks like. Notice that this whole side over here with the turbine and the water and everything, that still looks the same, but the whole other side changes because you have to have this really intricate, for a natural gas power plant, you have to have this really intricate design where like all this, liquid natural gas is like pumped through and like all this crazy complicated stuff happens. You could also have a nuclear power station, so all the stuff on the right stays the same, and it's the stuff on the left that changes. So you have this nuclear reactor, which is you have a nuclear chain reaction happening, like fission of uranium, and it's producing heat, and you're just using that heat to boil water. So it's the same setup, whether you're using coal or natural gas or nuclear power. The exact same setup is used for all of them. I don't know if you guys already knew this, but I remember when I first learned about this, I was shocked that like nuclear power plants, they just boil water. What? Like all this technology of like nukes and everything, and all it does is just boil water. I always thought that was really interesting. Here's a question for you guys: are there any thermal power stations that operate with renewable sources of energy? So can you think of any where this left half of the picture, where this left half of the picture is a renewable energy source? Can you guys think of any?
Biofuel?
Biofuel, sure, yeah, exactly. So like you just put some, ethanol or something like that you can grow off of crops. Biofuel for sure. Any others? Let me write those down.
Geothermal.
Absolutely. So as
Actually,
your
sir,
so as your heat source, you can use the actual heat of the earth. What did you say, Calvin?
it sort of circumvents the need to create the steam because it already generates steam as it's released up through the Earth's surface because it's boiling water underneath.
Yeah, so you can just like go like put it straight in there, like it's just naturally coming up. What's the problem with that though?
You have to dig into the surface of the Earth.
Yeah, there's a lot of upfront cost for digging in, but also not everywhere on Earth is going to be able to have that work. Like there's only
It
certain
would
spots.
it would be best to use it in places that have natural hot springs like Iceland, which
Exactly.
is
So
actually where the most use of geothermal is in the world.
yeah, exactly. And there's one other renewable source of thermal power stations.
Solar?
It is solar. Let me show you guys a few pictures. So this is a concentrated solar power plant. Jordan was talking about this last time, like when he drove down to the West Coast and he saw one of these things. So you have all these mirrors that are just concentrating all of this solar energy onto one spot. And then that one spot is filled with, I'll show you a schematic of how that works. So here's the spot where all the light is focused on. And you just take some material. I hear they're using molten salt and they pump it up into there and then that comes back down again and then that's your source of heat. So you're concentrating all that solar energy on some substance and you're heating it up and then you're using that heat bringing it back in and then once again here's your where is it right here, this is where the heat exchange is taking place, where that hot stuff, where is it, yeah, coming up this way, you feed it into this thing and then you have that going off to a steam turbine and everything like that. So you're just using the concentrated sunlight to heat something up and then go on. So this is a more complicated design. Like you could do this with water as well, but this using the molten salt is a little bit more efficient. And so that's what this diagram is showing you. But you could also do it with water. And then here's a geothermal power station. I believe this is in Iceland. I mean, just looking at the scenery there, it looks like Iceland. I noticed that there's like a lack of any sort of fancy looking equipment here. You just got some stacks with like steam going up into the air. This is the best picture I could find of a geothermal power plant, but you can see the whole like all this stuff up here stays the same, like with the generator and everything. And then the only difference is that now we're actually pulling the energy out from the ground, you extracting that heat and then dumping it back into the ground again to cool it off again. Cool. All right, let's talk about Sankey
Yeah.
diagrams. Sankey diagrams, you've probably seen these before. They're really famous, like around, like I just see them all the time, but maybe you just never knew they had a name. So they're called Sankey diagrams. It's an arrow block diagram representing energy flows. So the width of the arrow, like so how thick this is going to determine, it's proportional to the amount of energy that you're transferring. So if we start off with 100% of the energy on the input side, then you can see like where's all this energy going. So first off, about 20% of the energy is lost in the boiler. This is for a coal power plant. So 20% of the energy is actually lost through the actual, we'll look up at the boiler. I should have put, maybe I can like copy this down So if I take this and copy it, I'll bring it down here so we can look at it side by side comparison. And that did not work. Let's try this one more time. Doing it live. Okay, here we go. All right, so 20% of the energy is lost here in the boiler, and that makes sense because not all the energy from the boiler can go into the water. Like some of that energy is going to go out to the surroundings. You try to insulate it as much as you can, but still only 80% of the energy actually goes into the water. Okay, next, 40% of the energy is lost in the condenser, so that's over here. So we're having lots of energy coming out here as well that we're losing. And then 5 is lost to the turbine. So like mechanical resistance, like with friction of like spinning the turbine, you're losing some energy there too. And then finally, only 35% of it actually goes out to the electric grid. Oh, excuse me. So we want to calculate the efficiency of this coal power plant. So the way you find the efficiency of something is you take the amount that you get out and you divide it by what you put in. So efficiency, the efficiency is the useful output divided by the total input. So what's the efficiency of a coal power plant from this diagram? Tell me what to put for the useful output.
0.35 or something like that.
Yeah, let's calculate it. So what's the useful output? What do I plug in here?
35.
That's our useful output. The rest of this is getting wasted. Like that's literally being lost. So only 35 is going out to the electric grid. And then we're dividing that by our total input, which was,
It was 100.
and so that gives us 0.35.
35.
So the coal power plant is 35% efficient. That's quite low, very low. Most of the energy that was in the coal is lost. It is not transferred out to the electric grid. So it's a pretty inefficient process. It gets even worse though, like if you track the energy flow like all the way to a light bulb, let's say when you turn on a light switch. So we just talked about how you get that 35% here going out to the electric grid. Let's keep going. So you notice that 65% of the energy is lost at the power plant. 35% goes out to the grid. But then you have losses due to transmission, like going through the wires, distribution, like once you actually get it out from the distribution stations out to the homes. Then you have another loss in the wires in your house. And then when you actually turn on the light bulb, this is assuming you're using like an incandescent light bulb, like one of those old style light bulbs where they have like the filament across them. 28% of that energy is lost due to heat in the filament. So only 3% actually is light that's useful. The lampshade's going to absorb a little bit of that, and you're also going to lose a little bit of energy just to it like idling, and so you end up only getting 1% that actually goes into the illumination energy services. So this is a really sad thing because you're having to burn 100 times what you're actually getting, and this is just the sad reality of this is the law of entropy. Like you're going to lose energy as you go. Like you just can't, there's nothing that's 100% efficient. And so it's just the sad thing. If we look at this across our entire energy sector in the United States, every year the Lawrence Livermore National Laboratory releases this diagram. They just last month in March, they just released the one for 2019 because you got to wait for the year to pass before you collect all the data. But this is showing you the different sectors of our fuel sources and then how much of it actually gets rejected versus how much of it goes into energy services. And so one thing notice there is just how much of the petroleum, that's the oil, how much of that is going into transportation. It's like almost all of it. And then a little bit of it is going off to industrial uses as well. This is just like a really cool diagram. I'll link to this for you guys in the Google Classroom assignment. But if you want to make any comments about this, I'll just leave it up here for a minute if you guys want to say anything.
I feel like you don't hear as much about like hydro generation, but it makes up like twice as much as solar does.
Yeah, it does. That is interesting. Yeah, that we use more than twice hydro generation than from solar. That's crazy. But the hydro generation has been pretty constant. Like if you went back and looked at this chart like decades ago, it would have still been 2.5. Like there haven't been any like major new hydro projects in the US. Like we've kind of tapped it out. Like you found all the places where you can make dams and we've made them. There isn't really more energy to gain from that. Whereas with solar, if you went back a decade ago, that wouldn't have even been a one. It would have been like a point oh something. Like it would have been very, very small. So there are changes that are starting to happen, especially with wind. Like I remember the first time I ever looked at one of these diagrams, like back in the 2000s, the wind wasn't even on it. And just the fact that we're starting to see some changes, but it's very slow going. And the
There's a
coal
natural
has,
inherent weakness with hydro and geothermal energy sources. Is that the fact that they require specific area land
yeah,
types for them to work effectively?
yeah, that's a good point. That's really important to realize that. Like you can't just use hydro to fix all your needs because you just don't have access to those natural land features that allow you to have that energy source. That's really good, Kelvin. Thanks for mentioning that.
One of the best places in the world to build a hydro dam would probably be Angels Falls in Venezuela.
Oh, right. Yeah, that's like the in the Amazon, right?
Yeah, it's the tallest waterfall in the world.
Interesting. I assume that it would be a protected land space and you wouldn't really want to destroy the environment there, but yep.
It might be, but it's in Venezuela, so
Wow, Kelvin. So I told you
And
guys I'm gonna
would
I said I would show you the actual I'm gonna move on just for time, sorry guys. We could easily have a conversation on this in Discord if you want. Like you guys can just start typing in there now. I wanted to show you this graph because this isn't just the percentage of consumption. It's actually like the raw terawatt hours. So it's like a unit of energy. So like how much actual energy we're getting. And I just wanted to show this to you guys because I think it's a really cool graph. This is just for the United States. But you can see that natural gas is just like, boom, like shot up in recent, and coal has just plummeted recently. And the primary reason for that, and we talked about this last class, is just with the efficiency. It's like when you use a natural gas combined cycle power plant, you just get 60% efficiency, whereas the coal power plant is like that 35% that we calculated earlier. And as you can see from that, the like natural gas power plants are almost twice as efficient. And that's making it way more economically viable to build these types of power plants than it is for coal. And I think a similar shift is going to start happening. So if you notice like that huge shift there that we just pointed out is primarily economics because this combined gas power plant and the technology to build these plants in combination with the access to natural gas through fracking has just led to this huge explosion of coal dropping and natural gas rocketing up. And I think you're going to see a very similar thing happening within the next decade as it relates to renewable energies because now renewables are at the price point where it's actually cheaper to build a new renewable power plant than it is to build a natural gas power plant. And you're going to start to see a very similar effect happen, I hope, within the next 10 years. I mean, we'll see if I'm proven wrong, but I'm pretty hopeful about it. I just want to show you guys the combined cycle system of what makes this like why is natural gas so efficient? So like what is it about this combined cycle plant that's just so good at efficiency? And the what makes it efficient is that they have a heat recovery boiler. So there's not just like um, they actually take the exhaust. So like here's the what am I trying to say? The rejected heat, and they actually pump it back into the boiler. And so they're able to reclaim some of that rejected heat and put it back in again, and that actually just drastically increases the efficiency. Cars do this. It's called turbo, where you take like the exhaust and you punch it back in, and it gives you more efficiency. And this is just the king right now as far as U.S. production goes. I mean, obviously oil is more because of the energy we need to power all of our cars and airplanes and stuff like that. But as far as electricity generation goes, natural gas is one of the largest ones right now. Like you look at this blue right there, like we're definitely using a lot of natural gas, and the main reason for that is because of these new innovations in terms of increasing the efficiency of. Ooh, everything's lagging in terms of increasing the efficiency of those plants. Let's talk about nuclear power. Okay, so there's three things you guys need to know about with nuclear power. I'm just going to list them now so you remember. So we need to know about control rods, fuel rods, and moderators. So if you know about those three things, you understand nuclear power. So first up, you should know that there are two main designs of nuclear reactors. They are based on what's used to cool them or what's used as the moderator. And so there are two types of designs. There's the pressurized water reactor, which uses pressurized water as the moderator. And then there's this one over here, a gas-cooled reactor, which is using graphite as the moderator. So the basic idea is you have the reactor over here. This is the actual reactor, and then you have the heat exchanger, just like with a thermal power station. The difference, though, is that something special is happening inside the reactor. So what's happening is we're using uranium-235 with a neutron smashing into it to create fission, releasing all that energy. This is just like one example of a reaction that could take place inside the reactor. You'll remember we discussed this, a chain reaction. So those extra neutrons that come out of the reaction, so they're up here, those extra neutrons that come out, they can go on and collide with additional uranium nuclei to cause more fission, and that reaction just grows and grows. So this is called a chain reaction. And so this is what you need to happen inside a reactor, because this can be a self-sustaining process. So you just get it going and then it just keeps going by itself. So you don't have to like keep adding energy in to make it continue to go. It just goes on its own. It pushes itself. So the other thing you need to know about is that you need what's called a critical mass. So you can't just run a reactor with any uranium. You have to have a critical mass of uranium. So that's in order for the chain reaction to get going. So you can imagine if you have too small amount of uranium, the neutrons will escape without crashing in and causing more fission. The neutrons will escape. So if you just have a small amount, you can see like it's very easy for the neutrons to escape. Whereas if you have a larger chunk, a critical mass, then the neutrons are less likely to escape, and you're going to get that cascading chain reaction that you see in the picture right there. So for pure uranium-235, so like if you have a sample that's entirely uranium-235, which is not likely to happen because naturally, like if you look at uranium ore, it's like 99% uranium-238, and it's less than 1% uranium-235. So that's just like natural ore if you pull it out of the ground. It's not it's not going to work in a reactor. So if you let's say that this thing was pure uranium-235. So this is the uranium-235 is what you need. If it was 100% uranium-235, it would be 15 kilograms, like about a basketball. So like imagine like a basketball chunk of uranium. That would be a critical mass. If you're only 10% uranium, which realize that that's 10 times more than natural uranium, then it would take 130 kilograms. So you can see like you have to what's called refine or enrich. You have to enrich the uranium up to a certain amount of 235 before it'll actually be able to be critical mass that you can use in a reactor. The second thing you need to know is that uranium-235 will only capture neutrons if the neutrons are going not too fast. So if the neutrons are going too fast, it's not going to capture it. It's just going to like, it won't fission from it. You need those neutrons to go slow. So that means you need to add a material into the reactor that will slow down the neutrons. And so that material is the moderator. So what happens is you surround, so here's your fuel rod. So this is where your uranium-235 is. It's inside these fuel rods. You surround it with a moderator, in this case water in this reactor. And then when those neutrons hit the water, the neutrons will slow down so that they can be absorbed by the fuel rod, so that the neutrons can actually smack into the uranium right here. So the neutrons can actually smack in and then cause that fission to occur. So you have to slow down. You need to slow these guys down before the fission will occur. And you do that with a moderator. And so that's why you see two different reactor designs, one using water and then the other one using graphite. They both have their advantages and disadvantages. The main issue is that you're slowing it down through collisions. So like the neutron is crashing into the moderator, and then there's a transfer of kinetic energy. And then what's going to happen is the neutrons are going to slow down, but the moderator is going to speed up like the particles are. And so the moderator is going to get really, really, really hot, and you're going to need to like cool off or dump that energy somewhere. So obviously you send the moderator, you pump the moderator off into this heat exchanger where you can like boil water with it, but you're still going to have a lot of heat left over, and you're going to need to like dump that out somewhere. And so that's the main issue. That's what you've heard of like with reactors melting down and things like that. Is if the moderator gets too hot, the reactor itself can literally melt, and that's scary. The rate, like how quickly these reactions happen, is based on how many neutrons there are. So what you need to do is if the reaction is going too slow, then you can speed it up by just making more neutrons react. So if there's too few neutrons, the reaction will stop. If there's too many, it can lead to an uncontrolled release of energy. And so the way you fix this is with something called a control rod. And so that's what these green things are. So here's your fuel rods again. And so what you do is you just take these control rods and you go blomp, you like stick them down between the fuel rods, and then what the control rods do is they suck up neutrons. They just absorb neutrons. So when the control rods are all the way down, the thing is like pretty low, like there's not a lot of fission occurring. But if you lift up those control rods like over here, then the reactor is going to get really, really hot, and you're going to start to get a lot more energy being produced. So if you want to shut off a reactor, you just stick those control rods down there. They're usually lifted up by magnetic fields, so that way if there's like an emergency, they'll just like shunk and they'll just fall down and they'll just stop the reactor completely. But the moderator will still be really, really hot and you can still have a meltdown even if the control rods are all the way down. Here's some pictures of what reactors look like. So the control rods, this is just a cross section. This is what it actually looks like in reality. You can see all those rods there. Those are the control rods and the fuel rods. So you'll notice that you have lots of fuel rods. That's where all the uranium is. And then interspersed between those, you have some control rods. And those are the orange rods there. And then this is the last picture I'm going to show you guys today. This is the typical diagram that you'll see of a nuclear reactor. I got this off Wikipedia. Basically, you can see the moderator is surrounding the fuel rod. The moderators, through collisions, slow down the neutrons such that they can be absorbed by either the control rod particles or by the uranium to cause more fission. If the control rod is halfway down, you can imagine that you'd be absorbing roughly half of the neutrons, slowing down the reaction. If you put the control rod all the way down, you would be completely blocking the chain reaction from occurring. So what you want to happen is you want one of these neutrons to go and hit another uranium so that the reaction can keep going. And so the control rods are just going to basically determine how quickly that reaction can happen. So the higher we lift the control rods, the more likely the reaction is to continue, and the lower you put it, the less likely the reaction is to continue. That's nuclear reactor, guys. If you have questions, you should ask now. I covered a ton of crap, so jump in and say anything if you want.
It makes sense. Most of it is similar to what we learned freshman year when we talked about this.
Yep, I taught all of this in 9th grade.
I'm gonna go, Keppel. We have
Take care.
English.
Sounds good. Yep.
Thank you.
Later, guys. Have a great day, everybody. I'm going to start the recording now.